recording. That was recording.
What would happen, you came directly out of the drive and ran into the motor, you get up the front of the car, you come there. What they do when you barely speed driving, they'll run
Fluid power, we've already done that. So there's our motors, guys. One more thing, let me say, this is a stepper motor. So I got a circuit up here, but it's not working right. So this is a I didn't hook up the camera. We have two types of stepping motors. We have what we call a bipolar and another one called a unipolar. So what they're showing up here is a unipolar. So notice both the fields have the same polarity. So what we do on a stepping motor is this rotor is a permanent magnet. And then what we do is we electronically switch these fields, and notice we switch them in pairs. And if blue is north, then both fields are north at the same time. Now, the advantage of a unipolar stepping motor has, it's very easy to control. Because all we're doing is we're putting, this would be the two coils. They're wired in series with each other, but they're wired in the same direction, so they generate the same pole. But notice all we're doing with this guy is we're using transistors here to come up here and switch these coils either on and off, and we'll turn A on and B, C, and D will be off. Then we'll turn A off and turn B on, and all the rest of them be off. Then we'll turn C on, and all the rest of them's off, and then we'll turn D on. And what it does is it causes the permanent magnet in the center to do what? To align with those poles, but it moves in a step. A bipolar, which means this right here is the south, this is the north. This is the south, this is the north, and this is the north, that's the south. So this guy here is a lot of harder electronic control, because instead of just making everything north, we make them north, south, and then the next time around we have to switch it around, right? You understand? So the polarity switch around. Now, what's nice about a bipolar stepping motor, it creates more torque. So on one side you're pushing, the other magnet is pulling, right? You understand? So we get a lot more torque out of a bipolar stepping motor than we do a unipolar stepping motor. So the advantage unipolar is what? It's easier to electronically control. A bipolar, we have to use a plus and minus sign. When we switch this one negative, this is going to be negative, this is going to be positive. And we're going to switch the coil. So here's one of the coils right here. So we either turn this on and put a positive on this side, and we'll turn this on and put a negative on that side. The next time through, we'll put a negative over here and a positive there. If you can look at the control circuit as well, it's a lot more complex. So the stepping motor that we have is you can either wire it as bipolar or you can wire it as unipolar. Okay.
Talk about a single phase. So basically, the one is bipolar motor, those two are single phase motors.
These are DC motors. They're DC motors. DC doesn't have a phase. The stepping motors are DC motors. Now, what's nice about a stepping motor over a regular DC? What advantage does the stepping motor have over a DC motor? It's the regular DC motor. But it's a special DC motor. So normally when I say DC motor, I'm talking about either a shunt motor, a series motor, or permanent magnet. So stepping motor is a DC motor, but we don't say DC motor, we call it a stepping motor, right? You understand? It's just like Windows is a disk operating system, but we don't call it a disk operating system because the original operating system these things ran on, we called it DOS. But Windows is a disk operating system. Y'all understand that, which means the operating system is loaded off the disk. So a stepper motor is a DC motor. But we don't call it a DC motor, we call it a stepper motor. Well, the problem is if I use a regular DC motor, how am I gonna, if I want to set the speed of the motor, or if I want to know the position of the motor, that means what? We got to have some type of sensor out there, some type of encoder, or some type of tach generator, so I can set the speed. If I'm going to try to set the position, how do I hold the position? So when it gets to a certain position, how do I hold it? Well, if you take the voltage off the motor, it's going, all you got now is the friction of the motor, and a motor has very little friction. So it's hard to set the position on it. We can control the speed of a DC motor pretty easy. But as far as trying to make it get to a certain position and stop, that's the big problem we have with a DC. A stepping motor, all I have to do to make it stop is just stop the field. And if I stop the fields, I got two magnets locked on the two magnets, and the motor, it's got a really good holding torque, right? You understand that? Not only that, if I want it to move 40 degrees, all I got to know is the number of steps to send it to tell it to do what? 40 degrees. And then I send it so many steps, and it'll move 40 degrees. And when I get to 40 degrees, I just leave power on those coils. And now it's what? It's locked at 40 degrees. If I want it to go backwards, I just send the pulses what? The opposite direction. Go ahead. Tell me one.
I was just asking.
I'm asking you.
I mean, I don't know.
I don't know either. I'm not saying there's none out there, but I don't know of any other motor that you can set the position on it and you can do it openly. So stepping motor. So stepping motors become, so years we ran stepping motors open loop. Open loop means what? No feedback. Now, of course, you can get stepping motors with encoders on them. These guys are very powerful. Because the problem with a stepping motor, if something happens and it misses a step, you don't know it missed a step, right? You understand that? So we can get stepping motors now with encoders on them. The stepping motor, what we can do is we can find it one time. So you get over here and you look at that carousel, and the first time we turn it on, what does it do? It finds itself. And then after that, it's all steps. So if I want it to move 90 degrees, I wrote that thing so many times and it moves 90 degrees. And then I want it to stop. And I don't want it to move. Okay, so what do? They just leave power on those last coils, and then what does it do? It just holds that thing. Stepping motors have what we call a detent torque on them, so that's one of their specifications. It depends on the magnets. So when you turn this motor right here, turn it real slow, you can actually feel it locks into those pole pieces. Even though I'm not putting power on these wires right here, it wants to lock in on those pole pieces. We call that detent torque. That's how much it takes to cause it to turn if you don't have power on. And then we have locked in torque, which would be if I keep voltage on there, and that's really good. So you can actually feel the steps on this motor. And I'm trying to make this one step. So for years and years and years, when we first came out with disk drives, what they did was, I was going to show y'all some old floppy disks, the 3.5 inch disks. That's what they used to position the read-write disks. So they would actually step it, and we called them tracks. So if you had, if you had 100 tracks, then you'd have 100 steps. And each step would represent a track where they would record information. Of course, now stepping motors were really slow, so they went to what we call voice core, which is another closed loop system. So your hard drives now use a technique we call a voice core. We can take one apart and go into and look at that. So what do we use stepping motors for? Yeah, basically position and speed too. When you run them, they call it the slew rate. So when we go this thing around, we get to a point where it looks like it's running. It literally looks like it's running. It'll buzz at you, but it'll run real smooth. If you try to go above its slew rate, then it'll start missing steps and it'll start stuttering on you. So we can control the speed of the motor by how fast we move the fields around. We can keep up with where it's at. If we start from an origin, right, you'll understand. So your printer, odds are your printer uses a stepping motor on. So when you come up here and you turn that printer on, what does it do? You're going to, so it's finding zero. It's finding its origin. That's what it's doing. And then after that, we just move it with steps. We just step it across there, and we don't have to put any feedback on it. But what'll happen is if it's jammed up, you ever heard a paper jam? You can hear that thing still sitting in those pulses. They don't know it stopped. So what they do is they monitor the current to the motor. If it binds up on them, then they pretty know. Pretty soon, what usually happens is it'll get jammed, and then when it does a reset, it'll come over and hit that zero of that origin again, and it's never supposed to hit that again. So when it hits that, it knows it's what? Jammed, and then it can reset itself. So we use a stepping motor. There's no stepping motors on the Armatro line. There's no stepping motors on the Festo line, but we have one stepping motor on the Armatro line. So once it finds itself, then what does it do? We say, okay, I want to go 90 degrees. It knows how many steps that equals to what? 90 degrees. A CD reader can't do a stepping motor because a CD stores in a spiral. So a stepping motor would do steps. So they work real good on like old disk drives, because disk drives we do things in what we call tracks or cylinders. But a CD is a spiral, so it literally sits in the center and spirals out. So a CD or a DVD, of course, from the other out. So it's a very complicated task of monitoring the speed of that motor that moves across there, but it's just a DC motor. It's not stepping. But what's nice about a bipolar is that it creates more torque, right? You understand, for its size. But it's what? It's harder to electronically control. A unipolar, it doesn't create as much torque, but it's real easy to do what? Electronically control. So this is the circuit that controls a bipolar right there. Very, very simple. So I'm using a chip called a ULN 2003, which is another, what's that? Yeah, it's circuit for unipolar. I'm sorry. A unipolar is easier to control, electronically control, but it creates what? Less torque. So a bipolar, we literally have to swap the polarities of the coils while we're doing. Because not only are we pushing with one field, what are we doing? We're pulling with the other side of it. Normally you can tell these things because they sing at you when they run. Of course, when they're stepping, it's no big deal, but if they run them real fast, they'll sing at you. So some robots use them. Usually you tell them because in motion they go zzz, zzz. Those are usually using some type of stepping motor. So robots use either servo motors or stepping motors, depending on what type they are. If robots use it though, robots have to be so precise that they use feedback on all robots that I know. Well, all our robots are. This is a what we call a brushless motor. Now the problem with regular motors, and we got one over here. We'll take this apart. The problem with DC motors, normal DC motors, is that they have that commutator, and every time it goes between a segment, it creates a spark, which creates a lot of electromagnetic interference. So the problem is that they wanted to come up with a motor that had no brushes. So a brushless DC motor. So this is a DC motor, but it's got its own name, right? You understand? We call it a brushless DC motor. Okay. What it does is the rotor is actually on the outside. It's a permanent magnet. And what they do is they electronically rotate the center. What's going to happen is this magnet, part of the magnet, is going to latch into that, which is kind of strange for a motor because normally the rotor's on the inside, right? And we move the field. But this, on a brushless DC motor, the rotor is where? On the outside. We use this in all kind of computers because we don't want a lot of noise. So I guarantee you this has got a little old fan in there that blows it. I guarantee you it's a brushless DC motor. So any fan that's inside a computer will be a brushless DC motor.
I see like a car, the wheel, the motor, the electrical motor was the wheel, and that's what drives the car.
I can see that. I mean, that technique is something that's not new. So that's been around for years, huh? Well, they put a motor on the wheel instead of going through a gearbox. They call them locomotives. Locomotives have been using that technique for years. A lot of people think that most locomotives are electric. Most locomotives are electric. So they use the diesel to turn a generator, and then they put a motor on every wheel up there on that locomotive. Has its own motor on it.
Well, doing a lot of like heat water, stuff like that. Going over that.
I imagine they sell them up pretty good. I probably
They do, but
see
we
them.
had to stop the engine at that point and wait for it to come on. Back when I say, okay, you do that.
What's neat about electric motors is that if you put DC on the field on an AC motor, it literally turns into basically a shorted generator. And then when you try to load a generator down, it's going to stop things. So trains use something they call dynamic braking. So there's the big old things up on the front up there. If you open those things up, it's nothing but a bunch of resistors. And what they do is they'll take the AC off those motors. They'll slap DC on the stator, and then it'll turn into basically a shorted generator. And it'll load that sucker down. So most of the time, to slow a train down, they'll use what? They won't use the brakes. They use the brakes. They use those air brakes to stop.
Well, that just depends on not when you start, it's all not back.
Yeah.
That's
Chain. Yeah. And it's a pretty expensive, it's a pretty complicated control system on how to switch those things around. How they electronically control them. Brushless DC. So so this stepping motor, I can't get my circuit up here to work. I don't know what I've done. but I'll pass the stepper motor around. What did I do with it? And you can, huh? What I did? Did you feel it?
Yeah.
So you can literally, you can feel the steps. And that's the way that thing will work. Some reason I've got my thing out of step right here. I don't know if you can see it, but it's going back and forth, back and forth, back and forth, back and forth, instead of going around. Let's get do we have some jeweler screwdrivers? So what types of DC motors do we have? We got, here they are. We have shunt, series, compound, stepper motors, and brushless systems. Single phase motors, we have what? Capacity start, capacity run, split phase. Three phase motors. Three phase motors, it depends on how you wind them. Y'all call them motors. Why delta motors makes no difference. That's up to the manufacturer how there is no advantage of a Y motor over a delta motor.
Not in any industry? Aeronautics?
No, there's no advantage that I know of. I mean, it's just depending on where you come into play is what we call a Y delta motor. Y has more opposition, which means it draws if I put 240 volts across a coil of a Y motor, then the coils only see 120 volts. If I put 240 volts across the windings on the delta motor, it sees 240 volts, but at a lower current. So what we do with a Y delta motor is if we start at Y, then the coils see less voltage, and it produces less torque. So what we do with a Y delta motor is instead of having a reverse voltage starter, we switch it to a Y to start it, and then we switch it to a delta to run it. But a Y motor, a delta motor, has no advantage one over the other, because it's going to generate, if it's designed for 240 at 3 horsepower, then it's going to generate 3 horsepower at 240 volts. If it's a delta motor and it's 3 horsepower, it's going to be 3 horsepower at delta. And it's going to be less horsepower or at Y. So instead of having a reduced voltage starter, if we got a Y delta motor, we can start at Y and then run at delta. So it means we can run the motor without having any external component. We're going to talk about a wound rotor motor. You don't see hardly. So a wound rotor motor actually has a wound rotor. What they do is they control the resistance of the rotor, which controls the spring. Synchronous motors, what we do is we use a permanent magnet as the field. That's the rotor. If you use a permanent magnet as the rotor, that means you don't have to reduce the field easily. So a synchronous motor would rotate at the field speed. But you got to have slip rings on those motors. Because you put DC, you have to put DC. So that's all our motors have. Go ahead. So, yeah, but I think we've done everything on fluid power that we need to do, right? We'll do this. We'll do a circuit and do a pulse width modulation. The problem we have with DC motors, like shunt motors and our standard DC motors, shunt motors, separately excited motors, compound motors, and then permanent magnet motors, is that what we want to do is we want to control the voltage go into the armature. So how do I control the voltage go to the armature? So one thing we could do is I could come up here and I can use a rheostat. And this is the symbol, by the way, of the armature. And then I come over here and let's say this is 120 volts DC. So we control the speed by controlling the voltage on the armature. What's the problem with using a resistor? Right? I square R. Or if we put current through a resistor, it drops the voltage, and power is equal to V times I. So that means the resistor is going to get real hot. So that's wasted energy. So we could control the speed of a DC motor with a resistor. In fact, at US Steel, the big motors that was running the cranes, they had these big old resistor packs up there, and they had fins on them. They were so big. And what they would do is they would come up here and literally switch out resistors to run the motor at different speeds. So we had a 5-speed crane. So they went through 5 speeds, and that's all you was doing. You was jumping out the resistors. So the faster you wanted to run, the more resistors you ran. And when you jumped off all of them, the motor was running wide open. But the problem is that you're wasting a bunch of energy, right? You understand? So the watts being wasted by the resistor, you're still paying for those watts out there on that resistor, even though the only thing that thing's really doing is making heat. Well, it's got a job, right? You understand? But the energy that it's consuming is wasted energy. So we call these 5-speed cranes, and I don't know if you ever been on one. Up on that, it had the big old fins up there, and had them all closed off, and all the resistors. That's all they are was resistors. And then when you did your box up there, you picked up your radio receiver picked up that switched little peanut relays, and that switched medium relays and switched the big boys. That would switch those big old resistors in, because those guys had to handle a lot of current on a lot of those big old fans on the resistors, because we had to cool them down. Then we started controlling them electronically using transistors. But the problem with a transistor is it acts like a resistor, but we control it electronically. So this guy, I'd have to manually go up there and turn it, but a transistor, we can control its resistance with electronically, which is pretty neat. But it still drops the voltage. If it drops the voltage, then we have what? We have V times I. So we was putting these transistors on, we was mounting them on these big old heat sinks, because they was coming up here wasting power. It's just we went from this one, which was manually controlled, to this one, which was what? Electronically controlled. But what's nice about transistors is we can operate them like a switch. We call it saturation. Here it acts like a closed switch. And we can open it in cutoff. What do you think cutoff would be? What would it act like? Yeah, it acts like an open switch. So if I saturate it, how much voltage does a switch drop? None. So I could put 15, so we got I square R, so you got 15 squared times 0. How much power does a open switch? None, because we have no I. We have almost infinite R, but we have no I, right? You understand that? So we can operate the transistor in what we call the active region. In active region, it acts like a rheostat. But we can operate it like a switch. The problem is that it's not a perfect switch. So it always, even when it's saturated, it drops the voltage. but now we can electronically control that. So what we can do is we can turn it on or turn it off. So how do I control the speed? So if I turned it on, the motor would come on full speed. If I turned it off, the motor would turn off. So how do I control the speed? Well, it's either on or off. Well, what they did is they came up with this method called pulse width modulation, where we send pulses, we saturate the trend. So this is, you have to look at this as a current. Here's current's maximum. Here's current minimum. Here's current maximum. Here's current minimum. But what's happening is we're not changing the frequency. Notice the rising edges, they never walk. They never move. But what happens is that the DC motor sees that pulse width modulation as an average. And this on the right hand side is showing you the average. So right here, when the pulses get wider, the motor averages out to a higher DC. When it goes down, it's a lower DC. So what we can do is we can control the speed of the motor using pulse width modulation. And the transistors still get hot, but they don't get near as hot as running them. The problem we have is that when the voltage of the motor, there could be something to draw. So what we do is we come over here, the transistor's up here dropping all the voltage, and then it switches down. It can't do this at no time, right? You understand? And then what happens is the voltage across the motor does this. Well, let's see, this is the problem we have with the transistor. Right there we have I and we have an R, so you have power. So what happens is you still get hot, but it don't get near as hot as if I was trying to run it in the active region. And then plus we can control this electronically. So one of the most popular methods of controlling the speed of motor now is using what we call what? Pulse width modulation. Is that neat? So we'll show y'all this. Usually have to run it fast enough so the motor, if you run it real slow, you'd actually see the motor do what? Jerk. If you run it below 15 kilohertz, odds are you would hear the motor sing. You hear it go, because we can hear up to about 15 kilohertz. So normally they run them faster than that. Like I said, this is so popular. That microcontroller that I'm dealing with, the Arduino, has like 5 pulse width modulation pins on it that you can use to run DC motors with. So y'all go ahead and take a break, and I'll go and hook up the motor. I still can't get my stuff in motor. So we'll run a DC motor with pulse width modulation. So the period was equal to 10 seconds. And I don't know if this guy here don't have any graph paper on this. I know. So if the period was equal to 10 seconds, so we come over here, and if this was high 5 seconds. If it was low down here, we call it slow. If it was low for 5 seconds, then we would say this was we call it the duty cycle. So the duty cycle is the percent of the period that the waveform is high. And if this was 20 volts, then my motor would see this as 10 volts. So all we have to do, if we know the maximum voltage, what the motor sees is the maximum voltage times the duty cycle. Understand that? Real easy. It's a lot easier than trying to calculate the effective voltage of AC, right? Okay. So if I ran a 25% duty cycle, then it would be 25%. So all I need to do is change the duty cycle. So if I had 100% duty cycle, that means it's up here all the time, right? You understand? Then the motor would run at its maximum speed. If you have a 0% duty cycle, it's going to stop. And then whatever you put it between that would average it out. So all I'm doing here is I'm going to take the duty cycle, because right now it's running real slow, but I'm just going to go to a higher duty cycle.
That's maxed out.
I'm not running the motor at what's rated. Here's the way. Now, of course, this guy is a function generator. And this output and its frequency, I'm putting DC pulses on it. And I'm adjusting these. This guy can't run this motor. So what we do is we run it through a transistor. There's a transistor up here. And what a transistor does, it gives us a lot of current gain. So what I'm doing is I'm taking something that don't have the ability to run the motor, but I'm going to put my finger on that transistor. And guess what? It's not even hot. Why? Because it's either off or on. Now when it is on and it does have that crossover, that's when it dissipates the most power. And even when it's on, it's going to drop the voltage because it's not a closed loop. But what I can do now is this is an electronic device, and I can precisely control the speed of that motor by just changing the duty cycle. So this is probably one of the most popular ways now to control a DC motor. Pulse width modulation. So all I'm doing is changing the duty cycle. It's hard to see on the scope because the motor generates so much noise. If I disconnect the mode,
What do you got that magnet on top?
somebody put it on there.
Oh.
But it does affect the motor. Anyway,
Really?
what do y'all think?
No.
An easy person to blame.
The one that said, nah.
See, but what we're doing, you see, what we're doing though. So you can actually hear it slow down.
It does make noise. It's making noise.
And plus you can hear it. You can hear it change speed. So this is a 12 up motor injection, but I can't get the duty cycle on this down to 0.
Yeah, that's all you have hooked up is this.
Yeah, this is my stepping motor circuit that I can't get running. My motor steps twice and then comes back. Step on. I try to figure out what's wrong with it. I'll go to lab. Now this is an encoder. We're not using this, but I could take this encoder and I could take the encoder and run it through a controller, right, and actually control the speed just by changing the pulse width modulation. And what's so neat is that we can use pulse width modulation to generate AC, which is what they're doing now. But notice what they're changing. They're changing the what? The pulse width. They're changing the duty cycle, right? But here we're using a negative and a positive DC, and then my AC motor averages that out to a sine wave. Now it has to be filtered, but this is the way that a variable speed drive changes the voltage, and then it makes these, and then it changes the frequency to change the speed. And it changes them together. I couldn't find a animation that had both changing the frequency and changing the voltage. All I found so variable speed drives for AC motors use pulse width modulation. That's the most popular. They usually use transistors. They use a transistor called, when FETs first came out, instead of calling them MOSFET, we call them IGFETs, insulated gate field effect transistors. But after a while, the term MOSFET came into play, got very popular. Metal oxide field effect. Metal oxide semiconductor field effect transistor. Well, the advantage of MOSFETs over bipolar transistors is we can switch them faster. The advantage of bipolar transistors is that they can handle a heck of a lot more energy. So what they did is they combined a transistor, we call it an insulated gate bipolar junction transistor. So they've gone back to, and that's what most variable speed drives use. They either use transistors or they use the insulated gate bipolar junction transistor. But it's still using pulse width modulation to control those AC motors. And they can control them electronically. And the devices, since they're either saturated or cut off, don't produce near as much energy or wasted power as it would if we tried to run them in a linear or inactive region. You see, I can control the speed of that thing. You can actually hear it now. See, hear the speed up. And I'm not changing the height of the pulses. All I'm changing is the duty cycle. And the motor averages that out.
I thought it was lowered before when I was playing around with the light part.
Playing around with the light.
Yeah, and I was putting a light on it. Yeah.
Try that again.
At U.S. Steel, we call people like him knob kickers.
Yeah. Oh, we don't want to come in behind you. Oh, we come in behind you, we have all kind of things we have to turn.
What do they do?
They turn knobs.
turn
Turn down knobs.
Hey, let's see what this will do.
They got a screwdriver in here?
I'm sorry. Are we okay?
Yeah.
Pulse width modulation. Very powerful.
I want to do that. I want
I'll do what? I'll give you a circuit. You can use a 555 timer.
I have one.
I think I got the circuit somewhere.
Okay.
So what you do is, if you're familiar with the 555?
You can do a lot with it.
Yeah, what you do is, if you look at one side, you get a digital pulse. If you look at the other side, you get a slope generator, which is pretty neat. And then what you do is you put a rheostat on one input of the comparator, you put the slope generator on the other input of the capacitor on the comparator, and you compare when they match, and you generate a pulse. So you're not changing the frequency of the 555, you're just changing when you switch that thing on. Very, very cute little circuit called pulse width modulation. I'll try to find it.
Almost about that.
This is a stepping motor control circuit, and I was telling Thomas I've got it. I've got one that runs off that microcontroller I have, that Arduino. You'll still have to have the driver chip. This is one of these chips is nothing but transistors. Goes to Arduino one, puts out I think 20 milliamps, but they don't want you to overload the ports over 20 milliamps. So you can use one of these guys here to step it. I'll put that circuit up there too for you. In fact, that's it right there. That's one of them that I made. What we're going to do in the lab tonight, guys?